This third video of complex numbers Loci looks at this kind of situation where we have the modulus of z minus z1 equals the modulus of z minus z2. Now we could think of this being equal to a particular number, like equal to 3, in which case we're looking at a circle which is centered z1 of radius 3 and a circle centered z2 radius 3, and you can see that there are 2 points that would satisfy where the two circles meet. And if the circles were bigger, we would get 2 points further apart. So if you think of intersecting circles, they intersect at 2 points, and if you keep on increasing those, you get this perpendicular bisector, because these are the locus of points which are the same distance from z1 as from z2. So you can think of this as a circle, and this is a circle, and we get 2 points with the same distance. Or you can think of this as the loci of all the points which are the same distance from z1 and z2, and for each distance you get 2 points. 1 point here. Oops, let me just undo that. 1 point. Let's go back. So 1 point here. At a longer distance, 2 points here. Bigger distance, 2 points here. Bigger distance, 2 points there, and so on. Okay, so in this example here, we can think of if the modulus of z plus 1 plus I equals the modulus of z minus 3 minus I, the first thing to realize is that we need to write it as z minus z1, and so this is z minus 1 minus I equals modulus of z minus 3 plus I. So in this case, we label where these complex numbers are. Minus 1 minus I is here, and 3 plus I is over here. And so if we draw the line between them and then draw the perpendicular line to that bisects the point minus 1 minus I and 3 plus I, this will be the line that satisfies this Loci condition. Okay, and although we don't need to work out what the equation is in coordinates, we can do so, and it's also maybe helpful to understand how the complex equation relates to the Cartesian equation. All we do as before is that we let z equal x plus iy. So we're going to convert the real axis to an x-axis, the imaginary axis to a y-axis, and so we get the modulus of z plus 1 plus I becomes x plus iy plus 1 plus I is equal to x plus iy minus 3 minus I. And putting it into real and imaginary parts, we have x plus 1 plus y plus 1 I. Modulus is the same as x minus 3 plus y minus 1 I. And then the modulus of the left-hand side is going to be x plus 1 squared plus y plus 1 squared, all square rooted. But so will the right-hand side need to be square rooted, so I'm not going to square root. And on the right-hand side, we're going to get x minus 3 squared and y minus 1 squared. And both sides will be square rooted, but by squaring both sides, we end up with this. If we multiply this out, we get x squared plus 2x plus 1 plus y squared plus 2y plus 1 equals x squared minus 6x plus 9 plus y squared minus 2y plus 1. And we can see that the x squareds cancel, the y squareds cancel, moving, for example, all the y's onto the left-hand side, we have 4y. Moving all the x's onto the left-hand side, we have plus 8x. And moving all the numbers onto the right-hand side, we have 2 on the left-hand side, and we have 10 on the right-hand side, so we have 8. And if I then divide by 4, we have y plus 2x equals 2, which leads us to y equals minus 2x plus 2. Okay, and hopefully you can see that's the equation which gives us the same thing as we had earlier. And of course we could do it directly from the complex numbers, because 3 plus I is 3, 1. Minus 1 minus I is minus 1 minus 1. You could work out the midpoint, and the midpoint of those is 1 and 0. Is that right? Yes, I think it is. So it goes through 1, 0. And then you can work out the gradient. So there's the midpoint. And then the gradient of the line joining minus 1 to 3, 1 is equal to the difference in the y coordinates is 2. The difference in the x coordinates is 4. So the gradient is equal to 1/2. So the gradient of the perpendicular is equal to minus 2. And so the alternative method is that it's the equation of the line through 1, 0 with gradient minus 2, as you get y minus 0 equals minus 2x minus 1, which gives us y equals minus 2x plus 2. So we can see that we can get the equation of this line either by thinking only in terms of complex numbers, or by converting the modular statement into coordinate statement by letting z equal x plus iy. And that's it.